let me tell you a story about the founder of celestial mechanics, Johannes Kepler. Johannes Kepler was a German astronomer, mathematician, astrologer, and a natural philosopher. Also a writer on music. He is the key figure in the 7th century scientific revolution, best known for his laws of planetary motion and his books Astronomia, Nova, Harmonies Mundi, and Epitome Astronomia Copernicani. This presentation shows that Johannes Kepler is a brilliant astronomer. Let us now explore about his education and histories. In well-learned start, Nuremberg in the Holy Roman Empire of German nationality. He was a sickly child and his parents were poor, but his evident intelligence earned him a scholarship to the University of Tübingen to study for the Lutheran ministry. There he was introduced to the ideas of Copernicus and delighted in them. In 1596, while a mathematics teacher in Brahe who wrote the first outspoken defense of Copernican system, the Mysterium Cosmographicum, as university students. He studied the Polish astronomer Nicolaus Copernicus' theories of planetary ordering. Copernicus, 1473 to 1543, believed that the Sun, not the Earth, was the center of the solar system, a theory that contradicted the prevailing view of the era that the Sun revolved around the Earth. Kepler and Portuguese. In 1600, Kepler went to Prague to work for Danish astronomer Tycho Brahe, the imperial mathematician to Rudolf II, Emperor of the Holy Roman Empire. Kepler's main project was to investigate the orbit of Mars. Kepler was the assistant of Tycho Brahe, a freelance astronomer who worked before the inventions of the telescope. Kepler confirmed that Galileo's heliocentric view of the universe was correct. In the early 16th, Johannes Kepler proposed 3 laws of planetary motion. Kepler was able to summarize carefully collected data of his mentor, Tycho Brahe, with 3 statements that describe the motion of planets in sun-centered solar system. Kepler's effort to explain the underlying reason for such motions are no longer accepted. Nonetheless, the actual laws themselves are still considered an accurate description of the motion of any planet and any satellite.
Let's talk a little bit about Johannes Kepler. Johannes Kepler was Tycho Brahe's assistant, which is a Danish astronomer that collected all this data about the universe, the stars, the planets, and all these various motions. And he was trying to make sense of planetary orbits. Unfortunately for him, he was never able to complete the model because he died. And there's a rumor about his death that he was poisoned by Kepler. But this was never been proven. Okay, let's go back to the main point. Johannes Kepler picked all up what Brahe left, and he was able to come up with a model of planetary orbits, and this is what we are going to talk about. Kepler's law of planetary motion marked an important turning point in the transition from geocentrism to heliocentrism. They provide the first quantitative connection between the planets, including the Earth. Kepler's law of planetary motions are composed of three laws. Kepler's first law, also known as the law of ellipses, Kepler's second law, or the law of all equal areas, and Kepler's third law, also known as the law of harmonies. Let us talk about the first law. So, the first is, the orbits are elliptical, and they are elliptical with the sun at one focus. An ellipse can easily be drawn using two push pins placed on a straight line. Using a string, when the pencil is rotating around the push pins, ellipse is formed. Let us try to understand what an ellipse is. An ellipse is a closed curve into a two-dimension that looks like a stretched out circle. When the Earth moves around the Sun, the point where the Earth is closest to the Sun is called perihelion, and the point where the Earth is farthest is called aphelion. The first law states that orbits are elliptical. They are elliptical with the sun at one focus. So here's the sun, and the planet goes around like this. Sun is at one focus of the ellipse, and the ellipse has two foci. Here's one, and there's the other one on the other side by symmetry. The sun is at one of the focus. This is a big step because Brahe, Kepler's mentor, and the other people thought that they were circular orbits. And the reason why they thought about it is because when you look at the orbit of the Earth around the Sun, it is nearly circular, but the other planets have much more eccentric orbits. So let's talk about the equation for the first law. In analyzing planetary motion, it is more natural and convenient to take the origin of coordinates at the center of the Sun rather than using the center of elliptical orbit. Let us know that an ellipse is represented in polar coordinates radius and theta, and it's more convenient than using the x and y coordinates. So we take the ellipse by the following equation: r equals p over 1 plus eccentricity cos theta. P represents the semilatus rectum, and E represents the eccentricity. So what is an eccentricity? Let me explain something. Eccentricity predicts how much the ellipse is stretched out from a circle, and it takes a value between 0 for a circle and 1 for a parabola. As an ellipse is stretched out, it gets more eccentric, and the focus is farther away from its center. Alright. The second law that he came up with was the law of all equal areas. Equal areas in equal times. So what does that mean? So let's draw a planet there heading around. This means that this planet sweeps out this ellipse around the Sun. If I take a stopwatch and measure how far it moves at some amount of time, then I shade that area, I would get some number. But if I take the stopwatch and do the same amount of time at the four ends of its elliptical orbit, I'll get the same exact area. So this is 1 of an orbit, 1 month of an orbit, and this one is 1 month of an orbit. This necessarily tells us that the planet is moving slowest out here in order to get the same area, and in this region, it is moving fastest. Runs kinda sips in towards the Sun and goes back out, slows down, and comes and does it again. For a planet orbiting the Sun, r, or the radius, is the distance from the Sun to the planet, and theta is the angle between the planet's current position to its closest approach with the Sun as the vertex. So r represents the orbit size. So at a perihelion, theta is equal to 0 degrees and r is minimum. The equation for this is r minimum equals p over 1 plus eccentricity. At aphelion, theta is equal to 180 degrees and r is at maximum. The equation for this is r maximum equals p over 1 minus eccentricity. So the third law that Kepler came up with was a little bit more complicated to see. This was the law of harmonies. Period squared is proportional to the semi-major axis cubed. In words, that is it. And in math, it looks like this equation. In this equation, t represents the period. So for the Earth, the period would be 1 year. And what is this semi-major axis cubed? Let me explain something. Well, if I take my ellipse and I draw the bisector, this is the semi-major axis. The major axis is the length of the entire ellipse and semi-major axis is the half of it. Let us now discuss the rotation and the revolution of the Earth and the difference between the two, because some people get confused of these terms. For the rotation, let me simply describe it as transformation that turns a figure or object in either clockwise or counterclockwise direction. For a planet, the spinning of it around its axis is rotation. For the revolution, the movement of the Earth around the Sun in a fixed path is called revolution. The Earth revolves around the Sun from west to east, and it completes one revolution around the Sun in 1 year, or precisely in 365 days. Kepler found out that the period square was proportional to the semi-major axis cube, which is a huge step in understanding the motion of the planets. And what we're going to see is that, in fact, Newton's universal law of gravitation, that is what I am talking about earlier, can be used in deriving all Kepler's law. All Kepler's law is derivable from Newton's universal law of gravitation, and this is one of the reasons why these laws are important. And what amazes us is that Newton tied all up these planets, and he tied our entire solar system together with one law, which is pretty remarkable.